All right, so yeah, these notes are not in your book, so we're going to be just writing on a piece of paper, okay? The book didn't, I guess, deem this worthy of its time, so we'll just kind of do this on our own here. All right, so we're going to talk about polygons. And so we're going to define what a polygon is. So the word polygon, okay, comes from Greek. All right, and I believe it means, well, the word poly, does anyone know what that prefix poly means? Yeah?
Like many?
Yeah, many, exactly right. So poly just means like many. All right, and then the gon can mean something like sides or angles. I guess this like one term kind of can mean like two different things there. So like many angles or many sides, depending on, I guess, on the interpretation or something like that. Okay, so a polygon is just a shape that has many sides or many angles. Okay, so it is mathematically defined as a simple closed figure that is formed by at least 3 non-collinear points. And where they intersect only at endpoints. Okay, a simple closed figure that is formed by at least 3 non-collinear points and where things only intersect at endpoints. So like sides don't cross one another. Okay, sides don't cross one another. All right, so we'll ask ourselves, is it a polygon? And I got your homework too, so you're good. All right, so is it a polygon? All right, let's start with this shape. Is it a polygon? Yes. Excellent. All right. Is this shape? Is it a polygon? Yep, that's polygon, yep. No problem. Okay. Is this shape a polygon? It's supposed to be a circle. Is a circle a polygon? Yeah, no, okay, so it is not, and because there's no curves. Okay, we have to have straight sides, and the circle is only one big curve, right? And so we cannot, it's not a polygon because it's not made of straight lines, straight segments. Okay, let's see here. How about that shape? Yep, it's good. Okay, very good, yes. All right, let's see. How about this shape? It's made up of straight sides, though. It's not closed. That's right. So no, not. Oh, yeah. It's not closed. Not closed. It's open, not closed. Right? It's not connected everywhere. All right. Last one here. About that. No. Nope. Why not? Yes. It crosses itself. Okay. So no. It crosses itself. Okay, individually, if I like cover up this part, then that is a polygon. Or if I cover up this part, then that is a polygon. But to get taken together as one thing, it by itself is not a polygon. That's right. Okay. So We also like use a lot of vocab for the parts of a polygon too. All right. So, for example, and I'll draw a picture of a polygon over here so you can kind of like have something to refer to. And let's see, name some of these points here. A, B, C, D, E, F. Okay. So we have a polygon over here, and I've named it using letters and stuff. And let's see here. So one thing that we talk about sometimes is a vertex, or the plural is vertices. Okay. So a vertex, or vertices, and these are points that determine the polygon. Okay, so for example, we look at that polygon there, all right, and what points make up the polygon? Well, point A, point B, point C, point D, point E, point F. Those are also all called vertices. So you could say vertex A, vertex B, vertex C, D, E, and F. So that is a point, but also known as a vertex. And then collectively, they're known as points, right, or vertices. All right. I know this next one's going to be mind-blowing, right? Side, yes, okay, so it's the line segments that connect consecutive vertices. So consecutive, right, that means like in an order. So we don't just like willy-nilly connect points, right? A connects to B, B connects to C as well, C then also connects to D, D to E, E to F, A to F, F to A. And those all then make up the sides, right? So AB is a side, BC is a side, right? CD is a side, FE is a side, ED is a side, AF is a side. Okay. All right, so we talk about sides, and the reason why we talk about sides is because we also have another vocab term which is a little bit not so basic, and it's diagonals. Okay, and diagonals are line segments as well, but they connect. So it's line segments that connect two non-consecutive vertices. So non-consecutive. Okay. So Drew, can you give me an example of two non-consecutive vertices up there?
AE and AD.
Yep, AE. Okay. So we can just say, so like right there, from A to E, if we drew a line segment, that little line segment from A to E is a diagonal of the shape. Or AD, if you drew an AD, AD would also be, yes, a diagonal. Exactly right. Okay. Let's see here. The way we name a polygon, okay, if you remember when we talked about triangles, we talked about a name of a triangle, we put a little triangle symbol, and then be the three letters that make up that triangle, right? We don't really have a symbol for like a generic polygon because it can be all sorts of different shapes. And so instead, we just use the word polygon, and then we name it just like we do the triangle, we name all of its vertices. So you could name this triangle A, B, C, D, E, F. Sorry, not triangle, this polygon. Polygon A, B, C, D, E, F. Do we have to name it in that order? So what's another like order we can maybe use here? Let's go to, so like Adam, what's another way we can name this? Besides A, B, C, D, E, F, what's another way we can name it?
F, E, D, C, B, A.
Yeah, F, E, D, C, B, A. Okay, very good. What if I named it like F, C, D, B, A, E? Would that be okay? Yeah, no. We want to put those letters in order. You can start wherever you want. So you can start here, and then we've got to go around one way or the other way. You can't just like jump all around to the different points. You have to name it in the correct order that you see in the shape there. That's all. Okay. Okay. Let's see here. Let's see. Another thing we're going to do is classify polygons. Okay. Any questions so far? I guess I should stop and wait. I feel like this is pretty straightforward, so I hope I'm not rushing too quickly here. Am I going too quick for anybody? No? Okay. All right, good. I know it's a lot of writing, too, because we're not in the books. All right, classifying polygons. So polygons can be equilateral. All right. And equilateral means what? Anybody? All sides are congruent or equal. That's right. I'm going to use the congruency symbol there, just because I'm lazy and don't want to write the word out. Right. We can also have equiangular polygons, which we just know that means all angles are congruent. So if you remember when we talked about triangles, if a triangle is equilateral, we also knew the triangle was going to be equiangular, right? Is that true for polygons in general, though? If a polygon is equilateral, well, is it guaranteed to be equiangular? Or if a polygon is equiangular, is it guaranteed to be equilateral? And if not, can you think of the... So let's do the first one. Let's say if a polygon is equilateral, does it have to be equiangular? You don't think so? Okay, so do we have an example maybe or something? Of like a counterexample then? You think it does? So like if a polygon is equilateral, it's going to have to be equiangular.
Yeah.
Okay, so a square certainly does fit that. Yep. Mm-hmm. So can you think of a counterexample though? Okay, a regular hexagon? Or like so hexagons, I mean
like a soft line shape.
okay, octagons, but those could be equilateral and equiangular still. They could still be equiangular. Yeah, Lindsay? A rectangle. Okay, so what's a rectangle? It is, but, okay, so that's a counterexample here. So here's a shape that is equiangular, but not equilateral. What about the other direction, though? What if we have, can something be equilateral but not equiangular? Patrick?
A rhombus.
Yes, a rhombus, okay? So the easiest ones I think to think of are the ones that only have four sides. But a rhombus can be equilateral, but doesn't have to be equiangular, right? You can see that we're going to have some like obtuse angles and some acute angles there. Obviously, you have to trust my drawing, but take my word for it at least. Okay. All right. And then what's the word when something's both equilateral and equiangular? What do we call that? Patrick? Regular, which is such a silly name, I feel like, to call something so special, right? You know, something so special that it's both equiangular and equilateral. And we just call it regular. Okay. So both equilateral and equiangular. And then Shannon already took my question. She knows that a square is both equilateral and equiangular, right? That's the quadrilateral. And then we don't really have names for the other shapes if they're regular, besides just calling them regular. But the regular quadrilateral is a square. Okay. All right. That's one way to classify equilateral, equiangular, regular. We also have another way to classify, though, and it has to do with that question I asked at the end of the warm-up, too. Okay. So at the end of the warm-up, I asked you guys to kind of like try and figure out, or to come up with a way to describe that last one that was kind of bent in on itself. Okay? So we're going to talk about concave polygons. Okay? And a concave polygon it's a polygon that has at least one diagonal outside of the shape or figure. Okay. That has at least one diagonal outside of the shape. So let me show you an example of that. So for example, Okay, I draw this shape. Okay. So one diagonal I could draw would be like this diagonal right there. There's one diagonal, and that goes to the inside of the shape. But then if I were to connect another two pair of vertices, for example, if I connected these two vertices using a diagonal, that diagonal is outside the shape. Okay? Exterior diagonal. And so this shape is called a concave polygon. Okay, another example is something we saw earlier. Right, where it's kind of like, it's like bent in on itself. Okay, or you can think of it as being caved in. Concave is caved in. Maybe you guys have heard about this too, like in science. We talk about convex and concave lenses. Okay? Concave lenses are kind of bent in on themselves, or they kind of bend in. Okay? So there you go. And so then convex, this is an easy definition. Okay? Convex polygons are just not concave. Okay? If it's not concave, that means it's convex. Alright, and so, you know, you can just kind of like draw a little example here or something. Alright, you can see here that any diagonal that we draw, if we draw all the diagonals, okay, it's going to end up being a pentagram, so I don't know if it's like Illuminati confirmed or something like that, but there you go, okay? Alright, all the diagonals that we draw, they're all inside. All diagonals are inside. Okay? So that's the key. There you go. Properties, properties, properties. Alright, we already talked about names and things somewhat for the warm-up. We're going to do it again. Okay, so we're going to naming polygons now, finally. And then I'll have a little activity for you guys after all this business. Okay. So, 3 sides. Ooh. 3 sides means it is a what, Julia? Triangle. Okay. Gosh, my handwriting's getting like worse and worse, I feel like. Okay. 3 sides. 4 sides. Right, we already kind of saw that, but we'll do it again. Let's go to Hunter. 4-sided shape is called a quadrilateral. It's kind of interesting that a 3-sided shape we call a triangle, so it's 3 angles, but then a 4-sided shape we call a quadrilateral, so 4 sides. Oh, that's interesting. And then we completely break away from those kind of unique, those names. We go into like the more typical polygon names. So 5-sided shape, Drew, what's that? Pentagon, right? Like the Pentagon down in D.C., named for the shape of the building. Tanner, how about a 6-sided shape? Hexagon. Hexagon, right. And that comes straight out of the Latin. Straight out of the Latin. All right. 7-sided shape, let's go to Elizabeth. Do you remember? We talked about it. So I'm going to flip that quick.
Oh, septagon.
Septagon or heptagon, that's right. Okay? And you might be wondering to yourself, Mr. Widmeyer, September is not the 7th month. September is the 9th month. It used to be the 7th month. Exactly right. And October used to be the 8th month. And November used to be the 9th month. And December used to be the 10th month. But then Julius Caesar came along and made up 2 new months, and we made a new calendar, and so that's why we have the months of July, Julius, and then August, for I think it was like Julius Augustus, or Julius Augustus, I don't know, like Augustus is like his like title or something like that. So that's why we have the months of July and August, because the Emperor Julius Caesar. What's it? I feel like Augustus is like a...
There was like Octavius Augustus or something like that.
Okay.
His name, and then like Julius, like something like his last name, because
Yes, I think that's exactly what it is. Augustus is like a title almost, so yeah. But anyway, so yeah, something like that. But anyway, we added 2 new months, and that's why everything is now off. It's no longer September and October and November and December the 10th, and 9, 10, 11, 12, or 8, 9, 10, 11, 12 months. So 7, 8, 9, 10 months. Anyway, interesting stuff. So 7-sided. All right, so let's go. Let's see here. Well, we're going to continue on for a few more here. So 8-sided. How about Mary? What's the 8-sided polygon called? Octagon, right? Also, if you like to watch UFC, you can see them fight in an octagon-shaped arena there. Let's see here. How about Michael, the 9-sided shape? Ooh, now we're getting a little tricky here. Remember the 9-sided one? Nonagon. That is right. Nonagon. Okay. And let's see here. Oh, not here. All right. How about Lindsay? What, oh, you already know. Well, we already know this one, I think. We talked about it. But well, go ahead, Lindsay. What's the 10-sided one? Decagon. That's right. Okay. And then, believe it or not, I believe the 11-sided is the... Hang on a second. Let me write this down right. Undecagon? And then 12-sided, I know. For some reason I know 12, but I'm not as sure as about the 11. But the 12-sided is the dodecagon. Okay? And then really anything higher than that, it's just too ridiculous at this point. So for n number of sides, we just call it the n-gon. So for example, if we want to say the 99-sided shape, we just call it the 99-gon. And that's it. No special name for that. I mean, there might be a special name somewhere. I don't know. But that's as far as we get. Okay. And really, you don't need to really know the 11th and 12th sided one. I just wanted to put those in there for fun. And some of you thinking, Mr. Whitmire, you got a strange idea about what fun is. Maybe. Maybe. Okay. Questions on that then?
11 is hendecagon. Hendecagon.
Oh, so hendecagon. Okay. Oh, hendecagon. Hendecagon. Okay. And it's still then dodecagon then for 12. Okay. Interesting. So there are those. Now I have a little activity for us. We're not quite done yet, but I want to do this. Give you guys a chance to kind of like figure out something on your phone here. And so what we're going to do is try to calculate the interior angle sum of a polygon. And I don't think we've done this yet. So we'll see here. The directions are a little confusing, I think, so I'm going to give you guys, we're going to go over the first one. You have to go to the first kind of row there together. And I have you guys figure it out. Okay. So, gave you this shape here to try and find if there's a relationship for the interior angle sum of a polygon, right? So, for example, we know 1 for sure interior angle sum, and that is a triangle. If you add all the angles up in a triangle, we know that should add up to 180. Okay, some of you may also know for a quadrilateral what that's supposed to be. Does anyone know what is the quadrilateral's interior angle sum? It's 360 degrees. That's right. Okay, so we'll see that. So let's take a look at this. So in this sheet, they're going to be filling out here to kind of try and figure out that sum of the different shapes. We're going to name the quadrilateral, or name the shapes. Sorry, name the polygon. So this is 4-sided, so it's a quadrilateral. We'll tell the number of sides, so it's 4 sides. This next one might be the most confusing one about what to do. So it says number of triangles drawn from one vertex. What that means is pick a vertex of your shape. So I'm going to pick like this vertex right here, the bottom left corner, the vertex here. And I'm going to draw as many diagonals as I can from that vertex. Well, how many diagonals can I draw from this one vertex?
1.
Just 1, right? And it's going to go across like so. Okay? By drawing that one vertex, how many triangles have I drawn? 2 triangles. So that's the idea there. I've drawn 2 triangles, 2 possible triangles from that one vertex. Okay? And how many degrees are there in a triangle? We know that. It's 180, right? And so then what would we expect the interior angle sum to be of a quadrilateral? Well, if there are two triangles and each triangle adds up to 180, what can we do here to then get the interior angle sum? Yeah, do 2 times 180, and sure enough we get 360 degrees, which is what Maria said in the first place, okay? So go ahead and try and fill, or not try, please fill in the rest of that, okay? And see if you can answer the question at the bottom. If there's a pattern you see, maybe if you can come up with a formula to find the interior angle sum for any sided polygon, okay? So go ahead and try that, give it a shot. I'll kind of come around and help as necessary, or direct and stuff as necessary. But see if you can come up with the formula, because there is a formula.
How do you get degrees in a triangle?
Well, we know that this triangle's angle out is 180 degrees.
And so you
Because there's 2 triangles, so you multiply them by 2. So again, draw your diagonals in that one, take a vertex, draw your diagonals, see how many triangles you end up with. Yeah, how many triangles you end up with? 3. So you're going to put 3. And what are the interior angles? What's the degrees in a triangle? It's always 180, right? And what's the interior angle sum? It's about 10. You can see you can kind of come up with a general kind of formula. Any shape, any size, any emphasized shape. Okay. It's true. But what if I wanted to do like 90-sided shape? I want to find the interior angle sum. How do you find all ones before it and then add 180 to it, right? So maybe when you hold like a better way, so that way if I just tell you like, what's the interior angle sum for a 100 going? It's like, oh, I just, and you do it. Think about what you're doing, think of what you did. If I give you the number of sides, what you have to do first? I mean, like, so here, I give you the number of sides, 6. What you then have to do? And how many triangles were in the 6-sided shape? 4. So what can we do though? If I say 6-sided shape, how could you quickly tell me how many triangles are? Ah. So we take the number of sides, subtract 2, and then what do we do? Multiply that, answer by 180, right? Looks good. No, it's not. The only thing I'm going to say here is that if we, according to order of operations, the way you have it written, what are we going to do first? We do the multiplication first, right? So how can you guarantee you do the subtraction first? So far, so good. Yeah, looking good. So you should shape sides. It's like the number of sides in the shape.
Yeah, so I said 180 times 7. I think it would need to go with.
Oh. I don't, not quite. I think try it though. See. Okay. I don't think to get these numbers. So you get 540, for example. You did 3 times 180 at 540, not 5 times 180 at 540. Right, and we did 2 times 180 at 360, not 4 times 180 at 360.
I did something else.
Okay, so yeah, you might want to correct that. That's okay though.
So is that something?
Ah, okay, gotcha. Okay. Okay. So I'll fill these in here real quick. So pentagon, hexagon. Oops, see, I want to put the heptagon, octagon, and then 4, 5, 6, 7, 8, and then 2, 3, 4, 5, 6, and these are all 180. Okay, and then 540. I wish I had. 720. 900 and 1080. Okay. So there's our filled in sheet there. All right. And John, did you come up with like a formula here that relates the sum of the angle of the interior angle measures with like the number of sides or anything?
Well, I didn't do a formula.
Okay.
There's for every side that you add.
Yep.
Starting from the triangle, I guess it increases the interior sum increases by 180.
So we're adding a triangle. Each time we add a side, so for example, we went from 4 to 5 sides, we went from 2 to 3 triangles on the inside, and so that increased by 180 then. And then from 5 to 6, we add another triangle there from 3 to 4, and so that adds another 180. 6 to 7, 4 to 5, 7, 20 to 900, 7 to 8, 5 to 6, add another 180. That's right. Okay. So that's good. Yep. Very cool. All right, Elizabeth, did you come up with a formula we could use to relate maybe all these things together?
N-2 times 180 equals that.
Equals the interior angle something. That's exactly right. What's the n representing here?
The number of sides.
Number of sides. Yeah. If n equals the number, I'm going to use the pound sign for the shortcut for number. So, n equals number of sides, and so n minus 2 times 180 gives us the interior angle sum. Exactly right. Okay. So, with that in mind, then, when we go back to here, we'll talk about that just a few brief moments. Okay. So the interior angle sum for any polygon or I should say any convex polygon. We're not going to worry about trying to find an interior angle sum for concave because that's just, I don't think we could come up with something like that. Okay, is n minus 2 times 180 degrees, where n equals the number of sides. Okay. So we didn't get to this, but let's ask ourselves the question. So what is the interior angle sum of a decagon? Okay, so go ahead, take 30 seconds, figure that out. Okay, so again, what is the interior angle sum of a decagon? So what do all 10 angles in a decagon in a convex decagon have to add up to? So let's see here. Maria, you have an answer? 1,440, that's right. So 10 take away 2 times 180 equals 1,440 degrees. Okay? All right, so that's that. What about, though, here's a different kind of question. What is the measure of a single angle in a regular decagon? Now, how might we go about finding just one of them? We know what they have to add up to, right? We know the sum, but how do you find just one? Stephanie? Divide by 10. Why can I divide by 10?
Because that's how many sides
Sides, and also, therefore, the number of, since we're talking about angles, the number of angles as well. Okay? Why divide by 10, though? Why? It's a decagon. What else is true about this decagon, though? It's not just any old decagon. It is regular, which means what's true about all the angles? They're all the same. So yeah, so 1,440 divided by the number of angles, 10, gives us 144 degrees in the regular decagon. Okay? So there's an individual angle measure. Now, if the decagon were not regular, Stephanie, could we find the measure of just one angle, knowing the sum? Yeah, no, we couldn't do that, right? I mean, we would need to know 9 other angles to then find the 10th angle. That's possible. But if we don't know any other angles, we can't say what just a plain decagon's, individual angle measures would be. We need to know they're regular. That's how we're able to do that in the first place. Okay. So, questions on any of that? We're all good? All right, we're just about done here, just about done. I have one more little thing. All right, so we have interior angle sums. We also have an exterior angle sum as well. Okay. Okay, so, and basically, the exterior angle sum of a polygon is, and this is kind of interesting, 360 degrees. Notice I did not specify what kind of polygon we're dealing with here. It could be a triangle, a square, could be quadrilateral, square, quadrilateral. Could be a pentagon, a decagon, a 100gon, any polygon. If you add up all of its exterior angles, the exterior angles will always add to 360, no matter, and it's got to be a convex polygon, but no matter the polygon, it's always going to add to 360. Now, remember what I mean by an exterior angle. So, for example, here, if I have, let's just draw like a pentagon, maybe. Just kind of make things. Okay. So, an interior angle, right, is like this angle right here. The exterior angle is if I extend a side, then this right here is an exterior angle. Okay, or if I extend, this side, there's one right there. Okay. And you can extend any of the sides and you create exterior angles. Okay, like so. Those are the exterior angles. And they all will always add up to 360 degrees. So for a pentagon, all 5 will add up to 360 degrees. Now, what about this, though? What is the measure of one exterior angle of a regular pentagon? Okay, ideas here. How do we find the measure of 1?
22 degrees.
How'd you get that?
Well, if you add up 4 divided by 5, 360 divided by 5, 17.
That's right. Those 5 exterior angles, they all add up to 360, and if it's regular, that means all the exterior angles will be congruent as well. So yep, it's just 360 divided by 5, and it's 72 degrees. So each one of these should be 72 degrees if it's regular, just drawn, right? Okay. And then how can we easily find the measure of one of the interior angles then? At this point, what could we do? We have an exterior angle of 72 degrees. How do we find the easily interior angle? Yeah, just do 180, take away 72, because the interior and exterior are supplementary, right? If this is the interior and that's an exterior, they're supplementary. So just do 180 minus 72, and we get 108 degrees for the interior regular pentagon. And we can check that, okay, using our other formula. So 5 minus 2 times 180, that gives us 720. And divide that by the number of interior angles 5, and gosh, I hope I did that right. Did I do that math right? 3 times 180, 540. Whoops, I messed that up. It should be 540 there. There you go. Divide that by 5, and you sure enough get 108 degrees, which is the same thing. So 2 different ways to get those single interior angles if you want to. You can go about finding the interior angle sum, n minus 2 times 180, and dividing by the number of angles. Or you can find the exterior angles by just doing 360 divided by the number of exterior, and then find, using supplementary angles there, subtract from 180 as well. Either way, it works. Okay. Questions on any of that? So that's all I've got for you guys then. Let me end the video.